Hello everyone. In this video we'll be talking about array search methods. So the first method to search an array is linear search and the second one is binary search. In this video we will be covering linear search only. In the next video we will be touching the binary search. So let's get started. Suppose we have an array. We have an array and it stores these values 1, 2, 3, 4, 5, 6, 7, 8. Okay, it stores these values. Now what you are looking for is, you are looking for 4. You want to know, is 4 present in this array? If it is, then return me the index of 4. Where is the 4 stored? In the array. So let's create our linear search function. Let's create a function, static, it will return an integer value, static int, and let's name it as linear search. It will take in 2 arguments. First one will be an array that you are going to search, and the second one will be target, the number you are looking for. Okay. So how can we do it? Let's initialize a loop, for loop. Int I is equal to 0. Starting point will be from array at 0, and we will search up till array.length -1 and then I++. So what we want is, let's give it a target. Okay, int target is equal to, let's pick a number from you, 1, 2, 3, 4, 5. Let's pick in 5. Our target is 5. So we are searching for number 5. If array at I is equal to target, then return I. If array at I is equal to target, if array at index anything is equal to target, then return index. That's what we want. If in the whole array the target isn't found, like let's suppose I'm searching for 10, our target is 10, it's nowhere to be seen in this array. So in that case, just return -1. Return -1. Let's create a new variable, int index is equal to our function's name, linear search, and let's pass in our array, this array, and our target is equal to 5. What should the index of 5 be? Let's see. 1 is at 0th index, 2 is at first index, 3 is at second index, 4 is at third index, and 5 is at fourth index. Let's see, it should come out to be 4. Let's print out the value of index. Println index. Let's run this. 4. Our 5 is at array index 4. That's true. Now let's learn something about its time complexity. The algorithm we are using is linear search. Let's learn about its time complexity. Let me remove this whole code. So in linear search, what were our test cases? 1, 2, 3, 4 and 5, 6, 7, 8, 9. The search space is, the array's length is 9, sorry, the array's length is 9. So index starting from 0, it will search first 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8 and then 9. Suppose our target was 6. It will search index at first, then index at second. It will ask if index at second is equal to target. In this case 2 is not equal to 6, it will say no. Then it will proceed on to 3. It will ask if index at 2 is equal to target. In this case 3 is not equal to 6, it will say no. Then it will proceed on further. Say index at 3 is equal to target, it will say no. Then proceed on further. Index at 4 is equal to target, no. Then proceed on further. Index at 5, is it equal to target? Yes, it is. 6 is equal to 6. Then return the index. It will return the index. How many steps did it take to reach here? Index at 0, first step, second step, third step, fourth step and fifth step. It took 5 steps. So it took 5 steps. Some time was taken to complete a step. Some time was taken to complete a step, and it took 5 steps. It took 5 steps. So this will be our time complexity in this case. Time taken in one step into total steps, time into 5. Let's suppose the steps it took were n steps. In that case, the time complexity would be time into n, or in other words, it would be O of n. Time complexity is something else. We will cover it in some other video. For now, just remember that its time complexity is equal to time into n, time taken in one step into n steps. Suppose there were a million cases, like this array was a size of million. Then you would need to search each element, and the element you were looking for was at the very end of this array. So you would need to take million steps. In that case, time steps would be equal to million, and the time complexity would be equal to time taken in one step into million. It will be pretty huge. So what will be the best case scenario in this linear search? Let's suppose this is our array 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and our target is 1. Our target is equal to 1. Our loop starts from array at index 0 till array at index length minus 1. Array at index 0 is equal to 1. It will be like, is array at index 0 equal to 1? It will be like, yes, it is. Then it will return the index of that array. Cool. It will return 1. So the best case scenario will be, this whole algorithm will take only one step. This will be the best case. What about the worst case then? What will be the worst case? Suppose our target was equal to 10. Okay, our target was equal to 10. So in our for loop, it will start to search. Is our target equal to 1? No, it's not. Then proceed on further. Is our target equal to 2? No, it's not. Is our target equal to 3? No. Is our target equal to 4? No. Is our target equal to 5? No. Is our target equal to 6? No. Is our target equal to 7? No. Just like this, it will keep on asking this question till it reaches 9. Is our target equal to 9? No. Our target is not equal to 9. So the target wasn't found in this entire array. It wasn't found. So in that case, it will return -1, as we mentioned in the function. If target is not found, in the end, return -1. So it searched the entire array and didn't found the number we were looking for. In this case, it searched the whole array. The time complexity was time into n. Length of the array was 9. It took 9 steps. If the length of the array was million, it would have taken million steps. In that case, that time taken would have been very obvious. In this case, it was not that obvious. So basically, it's time complexity. Time complexity means time taken by one step into n steps in this case. Okay, this is a linear search time complexity. In the next video, we will be talking about binary search and how it's more optimal to use to search in an array. Till then, take care.